Welcome back to the Deep Dive. Today, we're embarking on a journey into a topic that isn't just timely, it's absolutely fundamental for anyone navigating a rapidly evolving world, driving digital transformation through cloud.
Yeah, it really is everywhere, isn't it? You can't escape it.
Exactly. And our core mission today is to cut through the noise, and deliver the crucial insights on the foundational lesson of digital transformation itself. Think of this as your essential guide, designed for you, the curious learner, who wants to be truly well-informed without getting bogged down in overwhelming technical jargon. We're here to give you the signal, not just the noise.
And for this deep dive, we're leveraging a truly robust and authoritative source, the Cloud Infrastructure and Services Version 3 Comprehensive Guide from Dell Inc.'s 2017-2018 revision. What makes this source so foundational and why we rely on it heavily is its strict adherence to the U.S. National Institute of Standards and Technology, or NIST, definitions for cloud computing.
NIST. Right.
Yeah, that means we're building our understanding on a rock-solid, widely accepted baseline. It's not just vendor hype.
Exactly. And our approach isn't about simply reciting definitions. We're going to extract the most important nuggets of knowledge, uncover some surprising facts, and hopefully infuse just enough humor to keep you engaged. We'll navigate this landscape one topic at a time in a logical, guided sequence, ensuring you grasp the strategic importance of this material. So let's begin. Kicking us off, let's talk about the absolute urgency of digital disruption. It's no longer a distant possibility. It's an undeniable force reshaping every industry right now.
Absolutely. It's happening fast.
Organizations aren't just contemplating digital transformation. They're at a critical crossroads where they must decide. Do they proactively become disruptors themselves or risk being disrupted by others?
It's truly a make-or-break moment for countless businesses. Our source highlights compelling data from IDC reports stating that by 2018, digitally enabled competitors disrupt 33% of all industry leaders.
Wow, 33%. That's huge.
It is. That's a staggering 1/3 of top players. And it underscores the sheer speed at which this transformation is unfolding. It's not about a single technology, but rather a powerful confluence of technologies like mobile, cloud, and big data, all accelerating at once, driven relentlessly by, ever-evolving modern customer expectations.
So these digitally enabled competitors, what are they actually doing differently?
That's the key question. Fundamentally, they're leveraging software in incredibly strategic and aggressive ways. They're masters at estimating future market requirements and spotting entirely new, often information-based opportunities. They deliver personalized experiences, much like the consumer mobile apps we all use daily, setting a whole new bar for customer interaction.
Like we just expect now, right?
Yeah, exactly. And critically, they innovate in an agile way, meaning they deliver better solutions incrementally and continuously, rather than waiting for massive, infrequent updates. Big bang releases are kind of out. This allows them to operate in real time, seizing fleeting market opportunities that traditional businesses often miss. And in an era of sophisticated security threats, they demonstrate transparency and build trust, which is a powerful differentiator.
That paints a vivid picture. But for you, the listener, why does this matter? Why should you care about these sort of abstract, digitally enabled competitors and their software-driven strategies?
Well, because this foundational understanding of digital disruption isn't just about growth, it's increasingly about organizational survival. Simple as that.
Yeah, it's the essential context for understanding competitive advantage in today's economy, isn't it? And it sets the stage for everything else we'll discuss. Now, let's shift our focus from those external pressures of disruption to the core business and internal IT challenges that are actually forcing organizations to transform from within. There are significant pressures on the business side that IT departments often struggle to meet.
That's absolutely right. One of the most pervasive challenges is the sheer explosion of data. Just think about the volume generated daily from web searches, social networking, emailing, uploading, downloading, media sharing.
Everything we do online.
Exactly. These activities are commonplace, and the data they produce has grown exponentially. This explosion drives an insatiable demand for anytime, anywhere access, enabled by the proliferation of internet-connected smartphones, tablets, wearable gadgets, and the Internet of Things, or IoT.
So constant access, more data.
Right. And this constant ubiquitous data access puts immense strain on existing systems. Compounding that is the real-time processing desire. Organizations increasingly need to process and analyze this data in real time or near real time to make immediate informed decisions. Decisions that can define market success or failure. And then there's the formidable challenge of predicting future business. With all these disruptive forces, traditional forecasting methods are kind of breaking down. Businesses need to fundamentally reimagine their future digital organization because accurately predicting and planning for new revenue streams is incredibly difficult.
So you need to be faster, too.
Precisely. This necessitates rapid new business establishment, the urgent need to develop new products and services as quickly as possible to capitalize on rapidly evolving digital marketplaces.
And it's important to remember that these growing business pressures are often severely exacerbated by internal IT challenges, right? It's not just that the demands are growing, it's that IT itself often isn't set up to efficiently meet them.
Precisely. Many IT departments are grappling with aging facilities and outdated policies, legacy infrastructure and rigid internal processes that simply hinder any real progress.
We've all seen that.
Yeah. We also see the rise of shadow IT, where frustrated business units basically bypass formal IT processes to acquire technology, creating unmanaged risks and inefficiencies that IT then has to somehow deal with later. Furthermore, existing IT equipment often suffers from scalability, security, and performance deficits, struggling to support the requirements of what our source calls third platform applications.
Just to clarify for our listeners, what are third platform applications? Can you break that down?
Good question. So third platform applications refers to the modern era of computing. Think mobile, social, big data, and cloud technologies. It's different from the old mainframe era, that's platform 1, or the PC client server era, platform 2. This third platform handles, billions of users and millions of applications, fundamentally changing how businesses interact with customers and deliver services. It's all about massive scale, instant access, and data-driven insights.
Got it. So those older systems struggle with Platform 3 demands.
Exactly. And continuing with IT challenges, traditional data centers are also frequently characterized by siloed infrastructure. Each application often has its own dedicated vertical stack servers, OS, networking, security, storage. While this might have worked in the past for individual apps, it creates immense operational and management complexities across the organization. Lots of inefficiency, slow delivery.
As a listener, I wonder if you recognize these symptoms in your own organizations or experiences. It's a pretty common story we hear, unfortunately.
Okay.
Let's unpack this. Given all those pressures and systemic challenges, what's the fundamental shift IT organizations must make to overcome them?
Well, the core transformation required is for IT to fundamentally shift from being a technology-centric organization to a service-centric organization.
Service-centric, what does that mean in practice?
It means IT should be managed like a true service business, accountable not just for costs, but for its efficiency and direct contribution to revenue. The focus has to change dramatically. It's no longer just about managing physical assets like servers or storage. Instead, it's about managing the supply and demand of business services. The ultimate goal here is enabling and achieving broader business objectives by being flexible, responsive, and consistently providing predetermined service levels to the rest of the company.
So IT needs to think more like a business unit itself.
Absolutely. This means IT needs to build products and services that directly support core business goals, like revenue growth, competitive advantage, customer retention, market share, regulatory compliance, the things that customers truly value and are willing to pay for. This makes IT a strategic partner. Critically, IT value and accomplishments need to be communicated in terms that actually matter to business executives.
Right, not just tech jargon.
Exactly. Instead of saying, we updated the server firmware, a service-centric IT should be saying something like, we enabled 20% faster customer onboarding, which directly contributed to X revenue increase this quarter. That builds confidence. It also means IT cultivating deep, proactive relationships with lines of business to truly understand their evolving needs, becoming an enabler, not just, a cost center buried in the basement.
That's a huge shift in mindset and purpose for IT, extending far beyond a simple technological upgrade. It's cultural. So with all these challenges and the imperative for IT to become service-centric, here's where it gets really interesting. How does cloud computing step in as the great enabler for all of this? How does it directly address those profound business and IT challenges we just outlined?
Cloud computing is uniquely positioned as the key enabler for both digital and IT transformation. It directly addresses the pain points we just discussed. First, it provides immense business agility.
Agility. Also,
by offering rapid provisioning of IT resources, often in minutes instead of weeks or months, cloud ensures quick time to market for new products and services. That significantly improves competitive advantage.
Right.
Secondly, it leads to a reduced IT infrastructure investment. Organizations can rent resources based on a pay-per-use or subscription model, effectively eliminating the need for large capital expenditures on, potentially underutilized assets.
Shifting CapEx to OpEx.
Precisely. This shift, in turn, leads to improved resource utilization, maximizing the efficiency of IT assets across the board. And finally, it results in a significant reduction of IT management complexity and cost by offloading many operational burdens like patching, maintenance, power, cooling to the cloud providers. IDC research powerfully reinforces this, stating that cloud computing has become an integral element of any successful digital transformation strategy. They also found that organizations that aggressively adopt cloud are 3x more likely than non-adopters to be approaching their digital business and infrastructure readiness goals.
3 times more likely. That's significant.
It really is. This isn't just a trend, it's a fundamental shift that correlates directly with an organization's success in digital transformation, which naturally leads us directly to the foundational understanding of cloud itself, what it truly is.
So if cloud computing is this critical enabler, we need to start with a solid definition. Why is the U.S. National Institute of Standards and Technology, or NIST, definition so important here? Why NIST?
Well, the NIST definition of cloud computing has become the de facto standard. It provides a neutral, authoritative framework that technology vendors, businesses, government agencies, everyone can basically agree on. It cuts through the marketing fluff.
Okay, so what is the definition?
NIST defines cloud computing as a model for enabling convenient, on-demand network access to a shared pool of configurable computing resources. Things like networks, servers, storage, applications, and services that can be rapidly provisioned and released with minimal management effort or service provider interaction.
Okay, that's quite packed. Let's break that down.
Let's do that. Configurable computing resources means we're talking about the whole gamut: networks, servers, storage, apps, services. The phrase rapidly provisioned and released highlights the speed and flexibility. That's the game changer compared to traditional IT procurement.
Right, minutes versus months.
Exactly. And minimal management effort or service provider interaction points to the self-service and automation that cloud computing delivers. You don't need to call someone every time you need a resource. In this model, you essentially have two main players: the cloud provider, which builds, operates, and manages the cloud infrastructure and services, and the cloud consumer, which is the customer using those services, whether they're external or internal to the provider's organization.
This definition truly sets the baseline for everything that follows in understanding cloud computing. It's the ground zero, you could say. So why did organizations move away from the traditional model of acquiring hardware and software? What was so restrictive about it, and how does cloud offer a better alternative?
Traditionally, acquiring IT resources meant, rigid procedures, lengthy approvals, and significant time, sometimes weeks or even months, just to get a new server or a software license.
Bureaucracy.
Yeah, lots of it. This severely delayed operations and increased the time to market for new initiatives. Cloud computing fundamentally transforms this. Instead of a large capital expenditure to buy resources up front, it shifts to an operational expenditure model where you rent resources on a pay-per-use or subscription basis. And critically, you can deprovision those rented resources when they're no longer needed, stopping the charges.
Yep.
You only pay for what you use when you use it.
That sounds much more efficient.
It leads to several powerful benefits: a significant reduction in IT capital expenditure, vastly improved resource utilization, and lower expenses related to managing IT infrastructure, like floor space, power, and cooling. Because the cloud provider handles many operational tasks, there's a huge reduction in IT maintenance tasks for the consumer, freeing up your team to drive new business initiatives and foster innovation.
So less time keeping the lights on, more time innovating.
Exactly. Think about needing a new server for a project. Traditionally, that meant weeks or months of procurement, approvals, setup. With cloud, it's literally minutes or hours via a self-service portal. That's the core difference and the real magic, if you will.
These benefits are truly transformative, but they're not actual magic, right? They're underpinned by very specific characteristics that make cloud, cloudy.
That's right. It's not magic. It's engineering based on these core principles.
So what does this all mean for how cloud works day to day? Let's really dive into NIST's 5 essential characteristics of cloud computing. These are the fundamental qualities that define a true cloud environment.
Okay, these 5 characteristics are what truly differentiate cloud from traditional IT, and they're central to the NIST definition. Let's go through them. First, on-demand self-service. This means you, as the consumer, can unilaterally provision computing capabilities, like spinning up a server or allocating storage, without needing any human interaction with the service provider.
So no waiting for IT.
Pretty much. It's like an app store for IT resources. A developer can get a new development environment in minutes without calling IT or submitting a ticket. It's about direct user empowerment.
Okay, number 2.
Next is broad network access. This simply means cloud capabilities are available over the network, whether it's the public internet or your private corporate network, and access through standard mechanisms like web browsers or APIs. This ensures ubiquitous access from anywhere on any device because applications and data reside centrally in the cloud. You can start editing a document on your tablet, then pick up right where you left off on your laptop, all without installing software on either device.
Makes sense. What's third?
The third characteristic is resource pooling. This refers to computing resources, processing power, memory, storage, network bandwidth being pooled together to serve multiple consumers using a multi-tenant model.
Multi-tenant, like an apartment building sharing resources.
That's a good analogy. These resources are dynamically allocated from the pool and then returned when no longer needed. Imagine a shared library where books, the resources, are checked out as needed and then returned for others to use rather than everyone owning their own copies. This is crucial for achieving economy of scale and high resource utilization for providers. Virtualization is often key here.
Fourth characteristic.
Fourth is rapid elasticity. This is the ability for consumers to quickly request and receive as many resources as needed up to a defined limit and then release them just as fast. It's about scaling out or in rapidly to match fluctuating business needs.
Scaling up and down easily.
Exactly. Preventing both over-provisioning, where you pay for idle resources, and resource shortages where performance suffers. Think of an e-commerce site. It can instantly scale up its compute resources to handle the massive surge in traffic during a Black Friday sale, and then just as easily scale back down afterward, paying only for what it used during that peak.
Very flexible. And the last one.
And finally, number 5, we have measured service. This means resource usage is monitored, controlled, and reported, providing transparency for both the provider and the consumer. Billing is based directly on consumption, for example, per gigabyte of storage, per transaction, or per hour of application usage. This is the core of the pay-per-use model that shifts capital expenditure to operational expenditure. It's like getting a detailed utility bill for your CPU hours, gigabytes of storage, or network transactions, so you know exactly what you're paying for. And it helps providers plan capacity too.
Got it. On-demand self-service, broad network access, resource pooling, rapid elasticity, and measured service. With these essential characteristics firmly in mind, let's explore how these services are actually delivered in the cloud. So now that we understand the core characteristics that make something cloud, let's talk about how these services are actually packaged and delivered. NIST defines 3 primary service models, but there's also an evolving 4th, ZACAS, that seems increasingly relevant.
Right. These service models basically dictate the level of control you, the consumer, have versus what the provider manages. It's a spectrum of responsibility. First, at the base level, you have infrastructure as a service, or ES. Here, you provision fundamental computing resources, virtual processing, storage, networks. You can deploy and run pretty much any software, including operating systems and applications.
So you manage the OS and apps?
Yes, you have control over those OS, storage, and deployed apps, but the cloud provider manages the underlying cloud infrastructure like the physical servers and networking. It's the most flexible model, essentially like renting virtual hardware. Classic examples are Amazon EC2 for compute and S3 for storage.
Okay, moving up the stack.
Moving up, we have Platform as a Service, or PaaS. In this model, you deploy applications you've created or acquired using programming languages, libraries, services, and tools supported by the provider. The key difference here is that you don't manage or control the underlying cloud infrastructure. No networks, servers, operating systems, or even the platform software itself.
So you just focus on your code.
Exactly. Your focus is entirely on your applications and their configuration. PS streamlines application development and deployment by abstracting away all that underlying infrastructure complexity. Examples include things like AWS Elastic Beanstalk or Microsoft Azure Platform Services.
Got it. And the top level.
The highest level of abstraction is software as a service, or SaaS. In this model, you simply use the provider's applications running on their cloud infrastructure, typically accessed via a thin client like a web browser or sometimes a program interface. You don't manage or control any underlying infrastructure or even individual application capabilities beyond, some basic user-specific configurations. It's a ready-to-use application. Think of Salesforce.com, Google Workspace, Microsoft Office 365. You just log in and use the software.
Okay, ISS SaaS. What about this SaaS?
Right, SaaS, which stands for Anything as a Service or Everything as a Service. This is more of an umbrella term. It definitely encompasses SaaS, PaaS, and IS, but it goes beyond that. It represents a growing smorgasbord of utility-based offerings that are accessed on demand over the internet. It reflects the continuous expansion of services offered via the cloud model, moving beyond just the traditional three, to include things like security as a service, database as a service, communications as a service, basically anything that can be delivered as a metered service over the network.
So the cloud model is being applied to more and more things.
Yeah.
Just as there are different ways to consume cloud services, there are also different ways to deploy the underlying cloud infrastructure itself, right?
Absolutely. The deployment model determines who owns and manages the infrastructure and where it resides.
With the service models clear, let's look at the deployment side. NIST defines 4 primary cloud deployment models, and we also see an emerging multi-cloud trend gaining significant traction.
Understanding these deployment models is crucial because they present different trade-offs in terms of control, scale, cost, security, and resource availability. First, the most common one people think of is the public cloud. This is cloud infrastructure made available to the general public, typically owned by a large organization selling cloud services, think AWS, Azure, Google Cloud.
Benefits being scale and cost.
Exactly. Its key benefits include low upfront expenditure and enormous scalability, often on a pay-per-use model. But there can be concerns around network availability, potential risks associated with multi-tenancy like data isolation, and sometimes limited visibility or control. IDC reports it's often chosen primarily for speed, cost savings, and agility.
Okay, exactly.
Then we have the private cloud. This infrastructure is provisioned for the exclusive use by a single organization, maybe across its various departments or business units.
So more control.
Definitely. It offers greater privacy and control over the infrastructure, applications, and data. It can be on-premise, meaning deployed within your own data center, or externally hosted, where it's outsourced to a provider, but the resources remain dedicated and securely separated from others. IDC suggests drivers for private cloud often include reducing total cost of ownership, TCO, over time, maintaining high performance levels, ensuring strong security, and keeping tight IT control.
Makes sense. What about community cloud? That sounds less common.
It is a bit more niche. A community cloud is set up for the exclusive use by a specific group of organizations that share common goals or requirements. For instance, maybe organizations in a specific highly regulated industry like finance or healthcare. Costs are typically shared among the community members. This model offers higher control and protection than a public cloud, but might be more expensive than public because fewer consumers are sharing the cost. Like private clouds, they can be on-premise or externally hosted.
All right. And hybrid cloud, we hear that term a lot.
Yes, the hybrid cloud is one of the most talked about models, and for good reason. It's composed of 2 or more distinct individual clouds, any combination of private, community, or public, that are bound together by technology, often proprietary or open standards, enabling data and application portability between them.
So best of both worlds, maybe.
That's the idea. Its properties like performance, cost, and security vary based on its specific composition, offering immense flexibility. It allows organizations to leverage the benefits of different models for different workloads.
What are some key ways organizations leverage hybrid cloud in practice? Can you give some examples?
Sure, there are some really common and powerful use cases. One is cloud bursting. This allows organizations to run their normal workloads on their private cloud, but temporarily burst into a public cloud to handle transient higher workload requirements, like seasonal peaks for retailers during the holidays. Another is web application hosting. Often, organizations keep mission-critical applications or sensitive data on a private cloud, while less critical or public-facing components, like e-commerce web servers or marketing sites, are hosted on a public cloud for better scalability and cost-effectiveness. Packaged applications like standard email or collaboration suites are often migrated to a public SaaS offering, freeing up private cloud resources. And application development and testing frequently uses the public cloud for its cost-effective elasticity, maybe moving tested applications to a private cloud for production or vice versa.
Okay, that makes the hybrid concept much clearer. And lastly, multi-cloud. How is that different from hybrid?
That's a good distinction to make. Multi-cloud approach isn't necessarily about having directly interconnected clouds like a hybrid setup. Rather, it's about consciously adopting multiple distinct cloud infrastructure services from different providers. The understanding driving this is that no single cloud model can suit the varied requirements and workloads of a modern enterprise. Different workloads simply perform better or are more cost-effective on different platforms. So an organization might use AWS for some things, Azure for others, and maybe a specialized provider for something else entirely. RightScale reports show that the vast majority of enterprises are heavily leveraging multiple cloud infrastructure services to meet their diverse needs. They pick the best tool for each job.
Got it. So it's about using multiple clouds, but not necessarily integrating them tightly like in a hybrid model. With these service and deployment models understood, let's look at how all these pieces fit together the cloud's architecture. So we've talked about the what and the why of cloud, the characteristics, and the different ways to consume and deploy it. Now let's talk about the blueprint. What exactly is a cloud computing reference architecture, and why is it so important for standardizing how a cloud environment functions?
Right. A cloud computing reference architecture is essentially an abstract model. Think of it as a standard blueprint designed to characterize and standardize how a cloud environment operates. It provides a common framework, a common language, for understanding all the moving parts. In a typical reference architecture diagram, you'll see core components like applications, the modern infrastructure that supports them, and that infrastructure itself includes physical, virtual, and software-defined layers. You'll see an orchestrator that automates processes and service elements that define what's actually being offered to consumers. Beyond these core components, the architecture also usually depicts crucial cross-cutting functions such as business continuity, security, and service management. And a key insight often shown is cloud extensibility, how it allows connection to external clouds, which is fundamental for enabling those hybrid models we just discussed. It's basically the foundational map for navigating the cloud landscape.
That makes sense. Let's start with applications then, as they are often the driving force behind cloud adoption and why organizations even consider these major transformations in the first place. How have applications themselves transformed alongside the IT infrastructure they run on?
Applications have undergone a really profound evolution. We can broadly classify them into traditional applications and modern applications. Traditional applications are typically monolithic, meaning they're built as large, single, tightly coupled blocks of code. This architecture leads to long development and update cycles, makes them incredibly difficult to maintain, and severely limits business agility. They are increasingly unable to support the rapid competitive market demands of the digital era. Think of older, complex enterprise resource planning, ERP systems that were maybe built decades ago for a much slower business pace.
Right. Hard to change, hard to scale.
Exactly. In contrast, modern applications, often called cloud native, are developed specifically to take full advantage of modern IT infrastructure. They typically adopt architectures like microservices and follow principles such as the 12-factor app methodology, which we can touch on. The impact of software applications is continuously increasing with digitization. Software has truly become a competitive weapon. Look at how companies like, say, Uber completely disrupted the taxi industry with a software-driven platform, or how GE now uses software for predictive maintenance on jet engines via data analytics from sensors.
So it's about software enabling new business models.
Precisely. These modern application-driven companies are characterized by compelling user experiences, responsive design across devices, and powerful data-driven insights. This is the kind of application transformation organizations are striving for.
This brings us directly to the evolution of IT platforms themselves. IDC talks about 3 platforms of IT growth. Can you explain what these are and why understanding them is key to driving application transformation?
Absolutely. IDC's 3 platforms framework is really useful for understanding the historical progression of IT and where we are today, which informs why transformation is needed. Platform 1 dates back to the mainframe era. Think huge, centralized systems supporting millions of users and thousands of applications, but relatively few compared to today. Platform 2 emerged in the 1980s with the PC and the client-server model. This supported hundreds of millions of users and tens of thousands of applications, much more distributed. Today, we are firmly in Platform 3. This platform comprises cloud, big data, mobile, and social technologies. This platform already supports billions of users and millions of applications, driven by pervasive internet connectivity, enabling unprecedented scale and agility.
And the challenge is running older apps on this new platform.
Exactly. The challenge is that traditional applications, often built for Platform 1 or 2, frequently impede agility and innovation in this new Platform 3 era. To overcome this, organizations need strategic approaches to transform their existing applications. Our source outlines 5 key R's for application transformation strategies. First is rehost. This is often called lift and shift, basically migrating applications to the cloud infrastructure, like IaaS, without significant modification. It's usually the fastest path to get something running in the cloud.
Okay, quick, but maybe not optimal.
Potentially, yes. Second is refactor. This involves actually re-architecting applications to truly leverage cloud-native features, like converting those monolithic applications into more agile microservices, maybe running in containers. More effort, but potentially more benefit. Third is revise. This means enriching an existing application by adding new modules and features using cloud services, but with minimal changes to the core legacy code. This often results in a kind of hybrid application. Fourth is retain. Sometimes you just keep certain traditional workloads in existing environments if they aren't suitable for the cloud, perhaps due to very old proprietary architectures or regulatory reasons. And finally, retire. Simply decommissioning applications that no longer provide business value. It's surprising how often this step is overlooked.
This framework offers a really strategic roadmap for organizations looking to modernize their entire software portfolio, giving them clear options beyond just move everything to the cloud now. Yeah. So if we're talking about building or refactoring into these modern applications, what specifically defines them? What's in their DNA, so to speak, and what principles guide their construction?
Modern applications are fundamentally different in their design philosophy and characteristics, really optimized for the cloud era. They prioritize a set of attributes essential for today's digital demands. They are built for speed, aiming to deliver services or updates in hours or days, not weeks or months. They emphasize resilience, meaning they are designed expecting component failures and can adapt on their own, continuing operation, even if a dependency is temporarily unavailable.
Built to fail, gracefully.
In a way, yes. Scalability is inherent. They support both predictive scaling, based on anticipated load, and reactive scaling, responding to current load, to handle fluctuating user demands efficiently. Their modularity architecture is key. They are component-based, distributed, and loosely coupled, very often built using that microservices approach we mentioned. And portability is critical, allowing them to run across different hardware platforms and, importantly, different cloud environments without major rework. They aren't locked into one specific infrastructure.
Okay. And to help build these robust applications, a well-known guide is the 12-factor app methodology. You mentioned that. Can you highlight maybe a few of the most impactful factors from that methodology?
Absolutely. The 12-factor app methodology is a widely accepted set of practices or principles for building modern, scalable, and deployable web applications or SaaS apps. While there are 12 factors, a few really stand out for their impact on achieving those modern characteristics. One is dependencies. Applications explicitly declare and isolate their dependencies, meaning they bundle everything they need or declare it via a manifest rather than relying on things being pre-installed system-wide. This prevents the classic, it works on my machine problem and makes deployments much more reliable and repeatable.
Ah, yes. Heard that one before.
Haven't we all? Another key one is processes. Applications execute as one or more stateless processes. This means any data that needs to persist across requests is offloaded to a stateful backing service, like a database or cache. The core insight here is that you can scale these stateless processes up and down instantly or restart them if they crash without losing critical in-memory state. This hugely enhances resilience and scalability. And a third one I'd highlight is dev-prod parity. This factor stresses keeping development, staging, and production environments as similar as possible. Same OS, same libraries, same backing services. The goal is to reduce the time and friction between code being written and code running in production, eliminating the nasty surprises that used to plague release days. It ensures what works in development actually works in production.
Those sound like really practical ways to improve reliability and speed. Breaking down modern applications further, let's focus on 2 core architectural components that really seem to enable this paradigm shift. Microservices and containers. You've mentioned them a few times.
Yes, these 2 concepts are absolutely foundational to modern cloud-native development and work very well together. Microservices architecture is a distinctive method of developing software where the application is decomposed into small, loosely coupled, independently operating services. Each microservice typically focuses on a specific business capability, runs in its own process, and communicates with others, often via lightweight mechanisms like REST APIs.
So breaking down the monolith.
Exactly. The beauty of this is that every microservice can be deployed, upgraded, scaled, and restarted independently of the others. This significantly speeds up continuous integration and continuous delivery CI/CD pipelines because you're dealing with smaller units. It also improves fault isolation, meaning if one non-critical service fails, the entire application doesn't necessarily come crashing down. It also allows different teams to work on different services independently and even use different technology stacks if appropriate, eliminating that long-term commitment to a single language or framework for the entire application. Think of a large streaming entertainment company like Netflix, which famously transitioned from a massive monolithic application to hundreds of microservices. This enabled them to achieve incredible 24/7 uptime, massive global scale, and rapid independent development cycles for different features like recommendations or billing.
That's a powerful example. And how do containers fit in with microservices?
Containers complement microservices beautifully. A container is essentially a lightweight, standalone, executable package that it includes everything an application or microservice needs to run. Its code, runtime, system tools, system libraries, binaries, and configuration files. Containers run on a host operating system and share the host's kernel, but their processes and resources are isolated from each other and from the host. This makes them far more lightweight and resource efficient than traditional virtual machines, which each need their own full operating system.
Lighter than VMs.
Much lighter. The open source Docker project really popularized containers and played a huge role in making them easily portable, allowing them to run practically anywhere on a developer's laptop, on-premise servers, or in any public cloud. This enables both rapid horizontal scaling, spinning up many instances, and seamless workload migration between different environments. Because they're so lightweight and start up quickly, microservices are often packaged and deployed inside containers. You can instantiate them rapidly, only when needed, and scale them independently.
Okay. Microservices for the architecture, containers for the packaging and deployment. With these advanced components in play, how do we actually develop these applications faster? That's where lean practices and DevOps come in, right?
Exactly. Having a right architecture is one thing, but you need the right processes to build and deliver software quickly and reliably on top of it.
So explain the core goal of lean practices when it comes to software development. It's about achieving high-quality software fast and at a low cost, isn't it?
That's right. Lean principles, originally from manufacturing but adapted for software, are designed to create more value for customers with fewer resources by focusing relentlessly on eliminating waste and enabling continuous improvement. This is a stark contrast to traditional linear development models, like the waterfall method, where development, build, test, and deployment happen in rigid sequential phases, often with long delays between them. While waterfall can eventually produce a full-featured product, it's often slow. Costs can be hard to predict accurately, and making adjustments late in the cycle is very costly and difficult.
Agile is the alternative.
The Agile model, which embodies many lean principles, is much more adaptive and iterative. It introduces limited sets of features per short development cycle or sprint, often with fixed resources and time. This allows for quicker feedback from users and stakeholders and makes it much easier to adjust direction based on that feedback. You build the most important features first and prove they are viable.
Okay. And building on Agile, we have DevOps, which has become pretty much the standard methodology for rapid application delivery. What is it and what are its core tenets?
DevOps is fundamentally a methodology or maybe even a cultural movement where software developers, Bev, and IT operations staff collaborate closely throughout the entire software lifecycle. It's really a framework for rapid application delivery that leverages both agile development practices and lean thinking. Its primary focus is on building an integrated automated toolchain that minimizes friction, issues, and defects, ensuring a smoother, faster flow from code commit all the way to production deployment.
And the benefits are significant.
The benefits are remarkable, yes. Studies, like Puppet's State of DevOps report cited in our source, show that high-performing organizations implementing DevOps can recover 24 times faster from failures and achieve 200 times more frequent deployments than their lower-performing peers.
Wow, 200 times more deployments. That's staggering.
It is. This is largely due to standardization, automation, and critically, a culture where people, process, and technology all work towards the same goal, breaking down the traditional silos and blame games between dev and ops. Critically, with DevOps, companies can focus more of their energy on developing new features and applications rather than just keeping the lights on with manual maintenance and troubleshooting. It boosts developer productivity by eliminating many manual error-prone processes.
A huge part of DevOps seems to be the concept of continuous integration. CI, and continuous delivery, CD. Can you elaborate on what these practices involve?
Absolutely. CI/CD are crucial technical practices that really enable the speed and reliability promised by DevOps. They transform how software is built, tested, and released. Continuous integration, CI, is a practice where developers frequently merge their code changes into a central shared source code repository, often multiple times a day. When these changes are pushed, an automated CI server detects them, checks out the code, builds it, and runs a suite of automated integration tests.
So finding problems early.
Exactly. It provides very early feedback if anything is broken, ensuring the main code base is always in a potentially releasable state. It relies heavily on automated testing and tooling. Continuous delivery, CD, extends CI. It enables teams to produce software in short cycles, ensuring that software can be reliably released to production at any time, often with just the push of a button. CD typically adds a more comprehensive, fully automated suite of tests, including things like acceptance tests and performance tests, and an automated deployment pipeline. Code that passes all automated checks is versioned and essentially always ready to be deployed. Updates can often happen seamlessly, sometimes even with zero downtime for users. The overall impact is immense. Release processes that used to take of manual effort can now take hours or even minutes. Developers spend more time coding and less time in endless integration meetings. User feedback gets integrated much faster, leading to building the right product for customers, ultimately increasing satisfaction and competitive edge.
This is truly how organizations achieve the agility demanded by digital transformation, speeding up everything from code commit to actual customer value. So to support this modern application paradigm, microservices, containers, CI/CD, what kind of infrastructure and platform are actually needed? What are the key attributes we should look for?
Right. You can't just run these modern applications effectively on old, rigid infrastructure. To truly enable them, the underlying infrastructure needs some specific attributes. It must provide high scalability and elasticity, allowing it to grow or shrink rapidly and automatically with demand. It needs to offer high performance for quick application response times. Application mobility and portability are crucial, allowing applications and their data to move seamlessly between different environments, like dev test and production, or even between different clouds. The infrastructure must inherently support continuous delivery pipelines and enable automated operations, removing manual toil and bottlenecks. And it should offer a choice of services, like databases, messaging queues, etc., and support a broad development framework to cater to diverse application needs.
What kind of infrastructure technologies embody these attributes?
Several key concepts come together here. Converged and hyper-converged infrastructure, which we'll discuss more later, provide modular building blocks that simplify deployment and scaling. Software-defined infrastructure, SDI, is another critical component. Using software to control compute, storage, and networking makes it more cost-efficient, often running on commodity hardware, and enables automation of configuration and delivery. This helps eliminate IT as a bottleneck. Critically, the infrastructure must be cloud-enabled, providing the capability to develop, deploy, and manage modern applications reliably and consistently, whether it's on-premise or in a public cloud. A key attribute enabled by these platforms is true portability. Imagine migrating a running application across different underlying environments, even between public clouds, with little or no perceived downtime. That's powerful. This portability also fosters collaboration between development and operations teams because they're working with a consistent platform. We also see infrastructure as code, gaining huge prominence, treating infrastructure configuration files using tools like Chef or Puppet, just like application source code, allowing for version control, automated testing, and automated deployment of infrastructure changes.
And all these principles, software-defined, automated, portable, lead to these powerful platforms, often called cloud-native platforms.
Yeah.
Can you define what a cloud-native platform is more formally?
Sure. A cloud-native platform is essentially an integrated stack, running from the underlying infrastructure all the way up through the application development framework and services. It's specifically optimized for rapidly developing, deploying, and scaling modern applications to meet fluctuating demand.
What does it offer developers in IT?
For developers, these platforms are fantastic because they typically support multiple programming languages like Java, Ruby, Python, Node.js, popular frameworks like Spring, and provide easy access to common middleware and backing services like MySQL databases, RabbitMQ message queues, Redis caches. For IT operations, it enables them to develop, deploy, scale, and manage the entire software delivery lifecycle much more quickly, reliably, and efficiently. These platforms often come with built-in resiliency and self-healing capabilities. They can automatically detect and recover failed application instances or underlying components, removing that burden from operators and ensuring rapid recovery times, maybe by automatically restarting processes or deploying new instances. They also typically offer dynamic load balancing, automatically distributing incoming user traffic across multiple healthy application instances, and dynamically updating writing tables if instances appear or disappear. Health monitoring is another core feature, providing deep visibility into the health of applications and the platform itself, enabling proactive actions to avoid outages. And robust or role-based access control, RBAC, defines precisely who can use the platform and what actions they are permitted to perform, granting permissions based on specific roles like developer or operator.
Can you give an example of a company using such a platform?
Absolutely. A great illustration mentioned in the source is a leading broadcast satellite provider, think someone like DISH Network, who partnered with Pivotal. They adopted agile development methods and utilized the Pivotal Cloud Foundry platform. This wasn't just a technology change, it involved a massive cultural shift. They literally transformed their office space, tearing down traditional cubicles and replacing them with collaborative pair programming stations, fostering a truly startup-like environment. They even had a guest developer program to spread the culture. This cultural change, combined with the power of the cloud-native platform, enabled them to dramatically accelerate innovation. They could quickly prototype and launch new applications, streamline sales interactions, and rapidly deliver new features with incredible speed and scale. Their developers could now focus on innovation, testing ideas early and often with real users, and delivering significant business value much, much faster.
That really shows the power of combining the right platform with the right culture and processes. So we have the architecture, the applications, and the development speed. But how do we manage all of this complexity in a dynamic cloud environment? That seems like the next big challenge.
Exactly. With all these dynamic pieces, elastic infrastructure, microservices, continuous deployment, managing it all effectively seems critical. Let's start with the basics. What exactly constitutes a cloud service from a management perspective, and how are these distinct from just, say, raw IT resources like a VM?
That's a key distinction. From a management perspective, a cloud service is truly a pack of IT resources made available to the cloud consumer by the cloud service provider. It's more than just the individual components. Once these resources are provisioned and configured according to a specific service definition, that service is instantiated as a service instance. Think of it this way. An IaaS service isn't just a random collection of virtual machines. It's a pre-packaged, potentially interconnected IT environment. For example, it might be 3 specific VMs configured for an application, its database, and a test server, maybe interconnected with specific virtual networks, VLANs, and attached to pre-configured storage, LUNs, all delivered as a single consumable unit of value.
So it's a bundle of resources defined for a purpose.
Precisely. Gartner even emphasizes this, stating that cloud computing deployment should begin with service definition, underscoring that IT organizations need to focus on delivering these defined cloud services, not just managing raw technology components. The service component in the architecture has 3 key functions: enabling the definition of services in a service catalog, allowing consumers to request and order those services, and enabling consumers to manage the service instances they've rented.
And the central point for consumers to discover and request these services is the service catalog, right? How does that work?
Yes, the service catalog is essentially the central source of information about all available cloud services within an organization or from a provider. It's like a menu, providing details on features, options, prices, and maybe even consumer-specific values or service levels. It typically includes elements like the service category, if your example, compute, storage, database, the specific service name, a detailed description, available features or configuration options, pricing models like per hour or per month, and estimated provisioning timeframes. Typically, consumers interact with this catalog through a web portal or an API, often using a web form where they can specify the requirements like the number of CPUs, amount of memory, or storage capacity needed for a particular service instance. It's really the self-service gateway for cloud consumption.
And once a service is ordered from that catalog, how do we interact with the cloud, both programmatically for automation and visually for users? What are the interfaces and portals?
Good question. Cloud interfaces are primarily web services, commonly based on standard web protocols like HTTP, using formats like SOP or REST. These APIs allow client applications like automation scripts, management tools, or even other services to programmatically request data and computations from cloud web servers and receive responses. This is how much of the automation and integration happens under the hood. Complementing these programmatic interfaces is the Cloud Portal. This is typically a web-based graphical user interface, GUI, that visually presents the service catalog and often provides access to managed resources via the underlying cloud interfaces. It's the primary gateway for human consumers to browse, order, and manage their cloud services. Administrators also use portals, often with enhanced privileges, to manage the underlying infrastructure and the lifecycle of the cloud services themselves.
So the portal acts as the front door.
Essentially, yes. It organizes and displays service information, handles user interactions, and sends requests down to the cloud's orchestration layer for execution. Modern portals are often personalized, tailoring the content and available options based on the user's identity, role, and access rights.
Okay, so from initial planning all the way through to eventual retirement, a cloud service goes through a comprehensive life cycle. Can you detail the 4 key phases of a cloud service's life?
Indeed. A cloud service isn't static. It follows a well-defined life cycle, typically broken down into 4 main phases. The first phase is service planning. This is where the strategic thinking happens. Cloud administrators and architects identify potential service offerings based on business needs, assess the current IT readiness versus the required capabilities, and define a service roadmap. This roadmap acts as a framework for the IT transformation journey. A critical activity here is developing the business case for new services, which justifies the necessary funding and clearly communicates the value proposition to executive leadership.
Getting the green light, basically.
Exactly. Next comes service creation. This is where the service is actually designed and built within the cloud management system. Key activities include defining service templates. These are collections of interrelated hardware and/or software components that constitute a service, for example, specifying standard VM attributes like processors, memory, disks, and maybe pre-installed software. Setting service attributes. These are the specific configurations or options available for the service components within the template. Defining service operations. These are the management actions that can be performed on a service instance, like add capacity, modify configuration, start, stop, or backup. These are defined as part of the template. And finally, creating service offerings. This involves combining the specific service templates with various constraints like access restrictions, operational policies like bandwidth quotas, firewall rules, quality of service, business rules like deployment or scaling guidelines, pricing models, and importantly, the service level agreements, SLAs, that define the guaranteed performance and availability. A formal service contract is also usually established, outlining the terms and conditions for using the service.
Okay, so planning, then creation. What's next? Seems like the big one is keeping it running.
You got it. The third, and often longest and arguably most complex phase, is service operation. This is where the rubber truly meets the road, day in and day out. How do we keep the cloud infrastructure and all those deployed services running smoothly and meeting their commitments?
Yeah, how do we do that?
Service operation management encompasses all the ongoing activities required to maintain the cloud infrastructure and the deployed services, ensuring that those committed service levels, SLAs, are consistently met. It's a continuous activity that needs to be optimized for the flexibility, complexity, and rapid rate of change inherent in cloud environments. While it can still follow established IT service management frameworks like ITIL, Information Technology Infrastructure Library, those processes must be adapted and heavily automated to support the cloud's characteristics like rapid deployment, elasticity, resource mobility, and self-service. It relies heavily on automation and workflow orchestration to keep up.
Okay, so service operation is key. Let's break down the crucial processes within that phase.
Yeah.
What are the main functions? Monitoring seems like a big one.
Absolutely. Monitoring, alerting, and reporting are fundamental. They are the eyes and ears of cloud operations. This involves continuously monitoring the status, performance, capacity, availability, and security of both the underlying cloud infrastructure and the deployed services themselves.
What's the purpose of all that monitoring?
Several key purposes. Monitoring data triggers automated routines, including recovery actions when failures occur. It provides the foundation for metering resource usage for billing and chargeback. It collects data for reporting on trends and capacity planning. And critically, it generates alerts when predefined thresholds are reached, policies are violated, or performance deviates significantly from the norm.
So it spots problems before they become critical.
That's the goal. Good monitoring tools need end-to-end visibility, need to collect data effectively in highly dynamic environments where VMs might appear and disappear constantly, store historical data for analysis, map services back to the physical components they run on, and do all this with minimal performance impact on the systems being monitored. Key parameters typically monitored include configuration, tracking changes, detecting errors or noncompliance, availability, tracking uptime, downtime, capacity, tracking resource usage against limits, performance, tracking efficiency metrics like response time and throughput, and security, tracking security events like unauthorized access attempts.
And the alerting part.
Alerting involves automated notifications, emails, texts, dashboard warnings sent when predefined thresholds or specific conditions are met. For example, you might get a warning alert if a server's CPU utilization hits 80% and a critical alert if it hits 95%. This prompts action before things break. And reporting takes all that monitoring data and formulates it into useful insights. This could be dashboards showing real-time status, trend reports for capacity planning, SLA compliance reports for business stakeholders, or cost reports for chargeback.
Okay, monitoring keeps an eye on things. What about keeping track of what's actually in the cloud environment? Assets and configurations.
That falls under Service Asset and Configuration Management, SACM. This process is responsible for maintaining accurate information on all the configuration items, CIs, in the environment. And CIs aren't just hardware. They include services, documents, software licenses, people involved, and even SLAs themselves, and crucially, the relationships between them.
So knowing how everything connects.
Exactly. Knowing things like which service instance a particular VM belongs to, or which consumer is using which service, or which physical server hosts which VMs, all these CIs and their attributes, like serial numbers, versions, locations, and relationships, are typically stored in a configuration management system, CMS, often a federated database automatically populated by discovery tools and periodically verified. It's the single source of truth about the IT environment.
And if we need to change something in that environment.
That's where change management comes in. Its goal is to oversee all changes made to any CIs in the environment to minimize any adverse impact on services. In a fast-moving cloud world, this process needs to be efficient. Low-risk, routine changes might have automated approval workflows based on predefined policies. More significant changes typically go to a Change Advisory Board, CAB, for review, assessment of risk and impact, and a formal decision. The aim is quick response where possible, but always minimizing risk, avoiding rework, and preventing service degradation. Change management tools help coordinate, track, and report on all changes.
Makes sense. What about ensuring we have enough resources but not too many? Capacity.
Right. Capacity management is crucial for cost effectiveness and performance. Its job is to ensure that the cloud infrastructure meets the required capacity, demands cost effectively, and in a timely manner. This means meeting peak demands without performance issues, but also optimizing utilization to minimize having lots of spare or stranded capacity sitting idle and costing money.
How is that done in a dynamic cloud?
It relies heavily on monitoring tools to gather historical usage data, establish trends, and perform predictive analysis for future demand. Strategies often involve leveraging resource pooling effectively, using automated VM load balancing to distribute workloads, thin provisioning of storage, allocating space only as needed, automated storage tiering, moving data to the right cost-performance tier, WAN optimization, and importantly, automatic capacity reclamation finding and decommissioning unused resources. For example, an orchestrated workflow might automatically expand a storage pool when capacity limits are approached, including getting necessary approvals and provisioning the new storage without manual intervention.
And performance management ties into that.
Yes, performance management works very closely with capacity management. It focuses specifically on evaluating the efficiency of services and components. It monitors metrics like response time, throughput, I/O wait times, CPU utilization, etc., to identify and proactively address performance bottlenecks before they impact users. Strategies might include policy-based VM placement, putting demanding VMs on faster hardware, automated storage tiering based on performance needs, data deduplication to speed up I/O, WAN optimization, and load balancing.
Okay, so we're monitoring, managing assets, handling change, capacity, and performance. But what happens when things inevitably go wrong? Incidents.
That's where incident management kicks in. Its primary goal is to restore normal service operation as quickly as possible within the agreed SLAs whenever an unplanned interruption or reduction in quality occurs. The process typically involves logging the incident, often automatically triggered by monitoring alerts, triggering automated resolution workflows if possible, or escalating to higher-level experts if needed. Sometimes it involves providing temporary workarounds if the root cause isn't immediately known. Key metrics tracked include service degradation time, affected components, resolution time, and severity. The history of incidents is a crucial input for the next process.
Which is problem management. How's that different?
Problem management takes a more proactive, long-term view. Its goal is to prevent incidents with common symptoms or underlying root causes from reoccurring, and to minimize the impact of incidents that cannot be prevented. It involves detecting problems, often by analyzing trends in multiple related incidents or investigating single high-impact incidents, diagnosing the underlying root cause, which might involve correlating alerts across different infrastructure layers, and then, if a permanent fix requires modifying the infrastructure, creating a request for change management approval. It's about fixing the underlying issue, not just the immediate symptom.
Got it. Incident is the firefighting, problem is the fire prevention. Now, what about security? You mentioned it earlier, but it seems critical enough for its own focus and operations.
Absolutely. Information security management is arguably one of the most critical aspects of cloud operations, forming the bedrock of trust. Given the distributed, multi-tenant, and often internet-facing nature of cloud, ensuring confidentiality, integrity, availability, and accountability of information is paramount.
What makes cloud security unique or challenging?
Cloud security encompasses all the practices and policies needed to protect applications, data, and infrastructure in this environment. But unique features of cloud, like rapid elasticity, extensive resource pooling, shared infrastructure, multi-tenancy, and self-service interfaces, create specific challenges and require tailored security approaches compared to traditional, static, on-premise environments. A key framework many organizations use is governance, risk, and compliance, GRC. Governance defines the policies and principles for security, ensures ethical conduct, and manages security aspects of contracts, especially with third-party vendors or cloud providers. Risk management is the systematic process of identifying potential security threats and vulnerabilities, assessing their likelihood and impact, implementing mitigation strategies like security controls, and continuously monitoring the risk landscape. Cloud insurance is even emerging as a mitigation option. Compliance focuses on adhering to external laws and regulations like APA for healthcare data in the US, GDPR for personal data in Europe, or PCI DSS for credit card processing, as well as internal corporate security policies. Compliance management ensures services and infrastructure meet these requirements. Standards like the Cloud Control Matrix, CCM, from the Cloud Security Alliance, CSA, provide frameworks for this.
And how are these GRC principles actually implemented? Through controls.
Exactly. Security is implemented through security controls. These can be categorized based on their function. Preventive controls aim to avoid security incidents, EVG, strong authentication, firewalls, encryption. Detective controls aim to detect incidents when they occur, for example, intrusion detection systems, security logs, audit trails. Corrective controls aim to reduce the impact of an incident and restore systems, EVG, restoring data from backup after a ransomware attack. These controls are delivered through different types of mechanisms. Administrative security, policies, standards, procedures like employee background screening, security awareness training, incident response plans. Physical security, protecting the physical data center, fences, alarms, biometric access controls, redundant power, and cooling. This is often a primary responsibility of the cloud provider in public cloud scenarios. Technical security, the tools and devices implemented on the cloud infrastructure itself. This is a huge area, including identity, credential, and access management, IAM, ensuring only authorized users access resources. Includes authentication, proving who you are, maybe multi-factor, authorization, what you're allowed to do, privileges, single sign-on SSO, and role-based access control, RBAC. Application security, building security into the software development lifecycle, SDLC, maybe using techniques like sandboxing to isolate untrusted code. Operating system hardening, reducing the attack surface of servers by removing unused software, applying patches promptly, and following security configuration checklists like those from CIS or DISA. Hypervisor hardening, securing the virtualization layer itself, which is critical in multi-tenant environments. Virtual machine hardening, applying hardening principles to individual VMs' network security, including firewalls, filtering traffic based on rules, maybe creating a DMZ for public-facing services, intrusion detection and prevention systems, IDPS detecting and blocking malicious activity, and network segmentation, isolating networks using VLANs or other virtualization techniques. Mobile device management, MDM, securing employee mobile devices that access cloud resources, and even security as a service, SESCAS, where the cloud provider offers security mechanisms like firewalling or threat detection as a consumable service.
Wow, that's a lot of layers. You mentioned shared responsibility earlier. Can you revisit that quickly? It seems crucial.
Absolutely. The shared responsibility model is critical to understand. Accountability for implementing these security controls varies depending on the cloud service model, IaaS, PaaS, SaaS, and the specific provider agreement. For example, in IaaS, the cloud provider is typically responsible for securing the underlying physical infrastructure, data centers, physical servers, core network. But you, the consumer, are responsible for securing everything you put on top of it, your operating systems, middleware applications, and crucially, your data. As you move up the stack to PaaS and SaaS, the provider takes on more responsibility, but the consumer always retains ownership and ultimate responsibility for their data and how it's used and accessed. You need to clearly understand where the provider's responsibility ends and yours begins.
What are some of the top threats people worry about in the cloud?
Our source highlights several key threats specific to or amplified by the cloud environment. Data breach. Unauthorized access to or disclosure of sensitive or confidential data, still a top concern. Identity, credential, and access management issues. Weak passwords, insufficient credential rotation, misconfigured permissions leading to unauthorized access, insecure application programming interfaces, APIs. As APIs become the primary way to interact with cloud services, vulnerabilities in them are prime targets. System and application vulnerabilities, exploitable bugs in operating systems or applications, just like in traditional environments, but potentially impacting shared infrastructure. Account hijacking, attackers gaining control of consumer cloud accounts through methods like phishing, keyloggers, or exploiting weak credentials. Malicious insiders, current or former employees, contractors, or partners misusing their legitimate access privileges. Advanced persistent threats, APTs, sophisticated, long-term targeted attacks often aimed at stealthily stealing large amounts of data over time. Data loss, not just from attacks, but also from accidental deletion, physical disasters, or software errors, highlights the need for robust backup. Abuse and nefarious use of cloud services. Cybercriminals leveraging the scale and anonymity of cloud resources, sometimes using free trials, to launch attacks like spam campaigns or DDoS attacks. Denial of service, DAX, distributed DDoS, overwhelming cloud resources with traffic to prevent legitimate users from accessing services. Shared technology issues. Potential failure of the underlying mechanisms that provide separation and isolation between tenants in a multi-tenant environment.
Okay, that covers the complex world of service operation. What's the final phase of the service lifecycle?
The fourth and final phase is service termination. This deals with the orderly end of the relationship between the cloud service provider, CSP, and the cloud service consumer, CSC, for a particular service. Reasons for termination can vary. Maybe the consumer simply no longer needs the service, it was only required for a temporary project, or perhaps the consumer is dissatisfied with the performance or support and is moving elsewhere. Key activities in this phase include securely deprovisioning the service instances, making sure resources are released back to the pool, and critically, handling the consumer's data according to the terms defined in the service contract. This might involve returning the data, securely deleting it, or providing proof of deletion. This is crucial for compliance. The provider typically also provides a final billing report and might ask for feedback on the service experience.
A clean shutdown. We've looked at the operations. Now let's talk about the foundational infrastructure choices that underpin all of this.
Right.
Before we virtualize anything or define it with software, let's get back to basics. What are the raw building blocks? The physical IT infrastructure, the actual compute, storage, and network components.
Absolutely. At the very bottom layer, every cloud environment, whether public or private, rests on tangible physical hardware. This includes compute systems. These are the servers themselves. Key components include the processor, CPU, random access memory, RAM, read-only memory, ROM, and the motherboard connecting everything. They come in various physical forms like standalone tower servers, space-saving rack-mounted servers that fit into standard racks, and very compact blade servers that share power and cooling within a chassis for high density. Storage devices. These are what actually hold the data. Common types include traditional hard disk drives, HDDs, with spinning platters, much faster solid-state drives, SSDs, using semiconductor memory with no moving parts, and older optical disk drives using lasers, storage systems. These aggregate and manage storage devices. We see network-attached storage, providing file-level access over standard IP networks using protocols like NFS or CIFS. We have block storage systems often accessed via storage area network, SCONN, using protocols like Fiber Channel or ISCSI, where the compute system manages the file system. And increasingly important is object storage, which stores data as objects with metadata and a unique ID in a flat address space, making it massively scalable and accessible via APIs like REST SOAP, ideal for unstructured data like media or backups. Network communication. This is the plumbing that connects everything. It includes compute-to-compute communication, typically IP-based using network interface cards, NICs, switches, and routers. And it includes compute-to-storage communication, which might be direct attached or more commonly in data centers via a SAN using fiber channel IP, ISCSI, or fiber channel over Ethernet, FCOE.
Okay, so those are the physical nuts and bolts. These components are the foundation. But you mentioned virtualization earlier as unlocking completely new possibilities. How did virtualization truly revolutionize IT infrastructure?
Virtualization was, and still is, a truly revolutionary technology. It's the process of abstracting those physical resources we just talked about, compute power, storage capacity, network bandwidth, to create logical software-defined versions of them. It was a game changer primarily because it allowed for significant consolidation of physical IT resources. Instead of one application per physical server, you could run many applications on virtual machines, VMs, on a single server, dramatically optimizing hardware utilization.
Getting more bang for your bucks.
Exactly. This, in turn, led to an increased return on investment, ROI, and reduced capital costs associated with purchasing new hardware, as well as lower operational costs for things like data center space, power, and cooling. It also simplified infrastructure management in many ways and greatly increased flexibility by allowing the dynamic creation, modification, and reclamation of virtual resources on demand. Virtualization is, in fact, a key enabling technology for those core cloud characteristics we discussed earlier, like resource pooling and rapid elasticity.
Can you break down virtualization for compute, storage, and network?
Sure. For compute virtualization, the core idea is decoupling the physical hardware from the operating system and applications running on it. This allows multiple operating systems, like Windows or Linux, to run concurrently as independent virtual machines, VMs, on a single physical system. This magic is enabled by a piece of software called a hypervisor. There are Type 1 or bare metal hypervisors that run directly on the hardware, and Type 2 or hosted hypervisors that run as an application on top of a conventional operating system. Each VM created by the hypervisor acts like a complete logical compute system with its own virtual hardware, CPU, RAM, NICs, disks, and is isolated from other VMs running on the same physical host. Our source mentions an educational institution case study. They faced infrastructure bottlenecks for students running high-performance engineering applications. Instead of buying expensive new physical workstations for everyone, they implemented a compute virtualization solution, providing virtual desktops running in the data center. This improved performance because they could dynamically allocate powerful virtual CPU and GPU resources as needed and significantly reduced IT support complaints.
Okay, that's compute. What about storage?
Storage virtualization applies similar principles. It abstracts the underlying physical storage devices, like arrays of disks, to create shared pools of storage capacity. Administrators can then carve out logical storage units, often called LUNs, logical unit numbers, from these pools and present them to compute systems. A key benefit here is that these virtual LUNs can often be dynamically expanded or reduced without disrupting applications. A common technique is using thin LUNs, which don't require all the physical storage to be allocated up front. Instead, capacity is allocated from the pool on demand as data is actually written, which greatly optimizes storage capacity utilization.
And network virtualization.
Network virtualization involves combining physical network components, like switches and ICs, into logical networks, or dividing a single physical network into multiple isolated logical networks. This is crucial for security, efficiency, and multi-tenancy in cloud environments. Common types include virtual LANs, VLANs for basic segmentation, private VLANs, PVLANs for more granular isolation within a VLAN, virtual extensible LANs, VXLANs, which overcome scaling limitations of VLANs for large clouds, stretched VLANs that extend layer 2 connectivity across different physical locations, and virtual SANs, vSANs, which do for storage networks what VLANs do for data networks.
It's clear that virtualization forms the very backbone of how the cloud serves multiple users dynamically, enabling that concept of resource pooling you mentioned earlier. So how exactly does the cloud serve multiple users dynamically using these virtualized resources? Let's revisit resource pools. What exactly is is a resource pool, and why is the engine of elasticity?
A resource pool is a really fundamental concept in cloud computing, enabled by virtualization. It's defined as a logical abstraction of aggregated computing resources, things like processing power, CPU cycles, memory, RAM, storage capacity, and network bandwidth that are gathered from multiple physical sources and managed collectively as a single pool.
So one big pot of resources.
Exactly. The key here is dynamic allocation. Cloud services obtain the computing resources they need from these pools, and resources are dynamically allocated based on consumer demand, often driven by policies or self-service requests. When a consumer releases these resources, for example, shuts down a VM, they are automatically returned to the pool, immediately becoming available for reallocation to other services or consumers. Resource pools are meticulously designed and sized by cloud administrators according to the requirements of the services they need to support. And these pools themselves are flexible. They can be created, removed, expanded by adding more physical resources, or contracted as needed. This pooling and dynamic allocation mechanism is precisely what enables the rapid elasticity and efficient multi-tenancy we discussed as core cloud characteristics. It makes cloud services incredibly efficient and responsive to fluctuating demand.
Okay. Building on virtualization and resource pooling, we arrive at the next major evolutionary step, the software-defined data center, or software-defined infrastructure. Why is software becoming the primary controller of infrastructure in today's IT world? What problems does it solve?
The shift to software-defined infrastructure, or SDI, is really a direct response to the increasing complexity, rigidity, and cost associated with traditional hardware-centric data center management. SDI is an approach that aims to abstract, pool, and automate all resources in a data center environment, compute, storage, networking, security to achieve IT as a service, ITS. Instead of manually configuring individual hardware devices, SDI uses intelligent, policy-driven software to control and manage the entire infrastructure stack.
What challenges does SDI specifically address?
It tackles several significant challenges inherent in traditional IT. Dealing with heterogeneous, multi-vendor IT environments where components don't easily work together. Breaking down siloed infrastructure where resources are dedicated to specific applications, limiting sharing, preventing unified management, requiring manual processes for provisioning, and increasing operational risk. Controlling rising operating costs associated with managing complex manual infrastructure. The key architectural shift in SDI is decoupling the control plane, where decisions are made, from the data plane, where data is actually forwarded or stored, and centralizing that control plane logic in a software controller. This allows policies to be defined and uniformly applied across potentially thousands of underlying physical components, and makes it much easier to upgrade or change control logic centrally through software updates rather than updating individual hardware devices.
What are the defining attributes of SDI?
Key attributes include abstraction and pooling, hiding the complexity of the underlying physical hardware and presenting resources as aggregated pools for consumption, enabling multi-tenancy, automated policy-driven provisioning. Services and resources are provisioned automatically based on predefined policies, including aspects like data protection and security, unified management, providing a single pane of glass or integrated toolset for managing compute, storage, and network resources together. Self-service, enabling consumers to request and manage resources themselves, typically via a service catalog. Metering, tracking resource consumption for chargeback, showback, and capacity planning. Open and extensible, often providing application programming interfaces, APIs, to allow integration with other tools and orchestration systems. Within the broader SDI concept, we have specific components. Software-defined compute, SDC, essentially refers to managing compute resources using hypervisors and virtualization platforms. Software-defined storage, SDS, uses an SKS controller software to manage storage operations independently of the physical storage hardware, abstracting details and delivering virtual storage schools and services. And software-defined networking, SDN, uses an SDN controller to manage switching and routing logic centrally, abstracting the network components and separating the control and data planes for greater flexibility and automation.
Can you give an example of SDI in action?
Sure. Our source mentions Colt Technology Services Group, a large global network and IT services provider. They successfully modernized their data center operations using Dell EMC VIPR, a software-defined storage platform. This allowed them to abstract and pool their diverse multi-vendor storage systems, automate provisioning, and offer storage services more efficiently to their customers, simplifying operations and increasing their business agility.
Okay, SDI seems like a powerful evolution. This leads naturally to the integrated infrastructure solutions that are gaining popularity, right? Like Converged and hyperconverged. Let's discuss the progression then. We went from building your own IT infrastructure from various parts to these pre-integrated solutions like converged and hyperconverged infrastructure. What's the story there? Why did this happen?
It's really a story about seeking simplicity, speed, and efficiency. Historically, as we touched on, organizations often took a build-your-own or best-of-breed approach. They'd select individual compute, storage, and network components from different vendors, believing they were getting the best in each category. While this offered maximum flexibility in theory, it incurred significant hidden costs and time delays. Think about the effort involved in evaluating different components, purchasing them, physically racking and cabling everything, testing compatibility, integrating them all, and then managing them long-term with multiple different vendor tools and support contracts. Scaling such an infrastructure also typically took a long time.
Sounds complex and slow.
It often was. This led to the rise of converged infrastructure, CI. CI solutions involve compute, storage, and network components, often from select strategic partners that are assembled, pre-configured, validated, and shipped together as a single integrated unit or system. Capacity can usually be added modularly by adding pre-validated blocks or components.
What are the benefits of CI?
Key benefits include much faster deployment times since much of the integration work is done by the vendor, easier scaling, potentially increased resource utilization, and significantly easier management, often through a single management software interface provided with the system. This can lead to reduced IT staff overhead, focused on just keeping the infrastructure running, reduced supply chain risk, fewer vendors to manage, and allows IT to focus more on innovation. There can also be cost advantages due to the pre-integration and optimized packaging. Architecturally, a CI system typically integrates those 5 logical sections: network, storage, compute, virtualization layer, and the management software.
Okay, that's converged. What about hyperconverged? How is HCI different?
Hyperconverged infrastructure, HCI, takes the integration concept a step further. HCI solutions typically pre-configure and manufacture compute, storage, and virtualization software tightly integrated into a single appliance or node. Multiple nodes are then clustered together to provide pooled resources. HCI delivers a validated solution with potentially even greater performance, simplicity, and scalability compared to CI. It achieves tighter integration between infrastructure resources primarily through software, building heavily on those software-defined infrastructure, SDI, principles we discussed. Storage is often virtualized using software running on the same nodes as the compute workloads, software-defined storage.
So even more integrated, what are the HCI benefits?
Benefits often include even simpler management, often a single centralized interface for the whole cluster, the ability to start small, maybe just a few nodes, and scale non-disruptively by simply adding more appliances to the cluster as needed, and being highly optimized for specific workloads like virtual desktop infrastructure, VDI, running business-critical applications, or deploying in remote offices or branch offices, robo, where IT skills might be limited. If you contrast CI and HCI, CI often provides hardware-based control and management integrated at the rack level, while HCI provides a more software-defined environment with tighter integration at the node or appliance level.
Can you remind us of the HCI example?
Yes, the rental service company mentioned in the source thinks someone like Rent-A-Center successfully deployed Dell EMC VxRail appliances, which is an HCI solution, for their VDI environment. Their choice was driven by the deep integration with VMware, which they already used, the promise of rapid deployment, simplified ongoing manageability, and high performance. This deployment slashed their administrative overhead for managing desktops and provided predictable costs for future expansion by simply adding more VxRail nodes.
That really highlights the buy approach. So what does this all mean for an organization facing these choices? Is it always better to buy one of these integrated solutions instead of building?
That's the million-dollar question, isn't it? The build-your-own BYO versus buy dilemma is a strategic decision every organization faces when implementing new IT solutions, and there are definitely clear trade-offs. For building your own, the main advantages are potentially complete control over every component and the ability to highly customize the solution to very specific or unique business needs. You might develop software perfectly tailored to your analyzed requirements.
But the downsides?
The disadvantages are significant. Building consumes a lot of internal time, resources, and money. It requires deep technical understanding of requirements, the underlying technology, and having the right skills in-house. You constantly need to keep pace with rapid technology development yourself. You bear the full burden of testing and integration. And crucially, it can be very slow to market, especially if requirements change quickly during the build process. For buying a solution like CI or HCI or even just standard servers, the advantages are that it saves time, resources, and often overall cost because the solution is readily available and validated. It offers much faster installation and deployment, and you typically get vendor support and maintenance included.
And the downsides of buying.
The main disadvantages are potentially less control over the specific components or underlying technology, and the risk of potential vendor lock-in, making it harder to switch providers later. Ultimately, the decision really comes down to several key considerations for each specific project. You must accurately identify and prioritize your business requirements. What problem are you actually trying to solve? You need to choose the right technology approach for those needs. Analyze existing solutions available in the market. Can something off the shelf meet 80–90% of your needs? Critically consider your required time to market. Do you have the luxury of building, or do you need a faster solution to remain competitive? And finally, honestly assess the availability of internal skills. Do you have the expertise to design, build, integrate, and maintain a complex custom solution long-term? This decision depends heavily on an organization's internal capabilities, risk tolerance, budget, and the external market pressures they face. There's no single right answer for everyone.
That's a great breakdown of the build versus buy decision. Now that we understand the infrastructure options, from physical to software-defined to converged, how do we protect it all and ensure it's always available when the business needs it? That seems like the next critical piece.
Exactly. We've built this potentially complex infrastructure, but how do organizations ensure operations continue even when things inevitably go wrong? Whether it's a small component failure or a major disaster like a fire or flood.
That crucial area falls under the umbrella of business continuity, BC, and disaster recovery, DR. They sound similar but are distinct. Business continuity is really about proactive planning and preparation. It involves identifying potential threats to operations and putting measures in place before anything happens to minimize the impact of any service disruptions. The ultimate goal of BC planning is ensuring continuous service availability, or at least minimizing downtime to acceptable levels. Disaster recovery, on the other hand, is more reactive, although it relies heavily on the proactive BC planning. DR is the coordinated process of actually restoring IT infrastructure, applications, and data after a natural or human-induced disaster has occurred. This often involves activating resources at a secondary data center or location to take over operations from the primary site that was impacted.
So BC is the plan. DR is executing part of the plan when disaster strikes.
Largely, yes. For example, if a major disaster like a hurricane hits one data center, the overarching business continuity plan would likely trigger a specific disaster recovery process. This might require transferring users, critical data, and essential services to run at another pre-designated location, ideally with minimal data loss and downtime.
A key metric underlying both BC and DR seems to be service availability. What does highly available truly mean for a cloud service, and how do we measure it? It's not just up or down, is it?
No, it's usually much more nuanced. Highly available refers to the ability of a service to perform its agreed function according to the business requirements and customer expectations during its specified operating time. It's not just about being reachable, but about performing correctly. It's often measured quantitatively and expressed as a percentage of uptime over a given period, frequently using the nines notation. For example, a service advertised as having 5 nines availability means it's guaranteed to be available 99.999% of the agreed service time, e.g. over a year.
5 nines sounds impressive, but what does that mean in real terms?
It translates to very little downtime. 5 nines availability allows for only about 5.26 minutes of downtime per year. Compare that to, say, 2 nines, 99% availability, which allows for over 3.6 days of downtime per year. Our source gives an example. 99.18% availability for a 24/7/365 service still means approximately 3 days of downtime annually. So those extra nines make a huge difference, but they also typically come at a higher cost.
What causes services to become unavailable?
Unavailability can be caused by a wide range of factors. Obvious things like hardware resource failures, compute server dies, storage array fails, network switch goes offline, but also poor application design that doesn't handle errors gracefully, resource configuration errors made by administrators, software failures or bugs, and sometimes even planned routine IT activities like system upgrades, migrations, or maintenance if they aren't managed properly with redundancy and failover mechanisms in place. Solutions for improving availability and protecting data involve a multi-layered approach. deploying redundancy at both the component level, for example, dual power supplies, RAID storage, and the site level, multiple data centers, utilizing robust data protection solutions like backup and replication, which we'll discuss more, implementing automatic failover mechanisms so systems can switch to standby resources without manual intervention, and architecting resilient cloud applications designed to tolerate failures.
Okay. To truly achieve that high availability, we need more than just the ability to recover after something fails. We need systems that can continue working through failures. That sounds like fault tolerance. What is it, and why is it so crucial for cloud environments?
You've hit on a key concept. Fault tolerance is defined as the ability of a system to continue functioning, possibly at a reduced level, even when a fault situation occurs, or during the failure of some of its components. It's about designing systems to withstand failures without causing a complete outage. It aims to protect against various types of unavailability, transient, short-lived glitches, intermittent failures that recur periodically, and permanent component needs replacement.
How is fault tolerance achieved?
It can be achieved through specialized hardware, sophisticated software techniques, or often a combination of both. It's important to note that achieving higher levels of fault tolerance usually incurs higher costs. There's a definite cost-benefit trade-off as you strive for that elusive 100% availability. The core principle underlying almost all fault tolerance techniques is redundancy, having duplicate or alternative components or paths ready to take over if the primary one fails. Fault tolerance improves both the reliability of a system, its ability to perform consistently as expected, and its availability, its ability to perform its functions during its operating time.
Can you give examples of fault tolerance techniques at different levels, maybe infrastructure first?
Sure. At the infrastructure level, we build redundancy into the core components. Compute clustering. Grouping two or more compute systems or hypervisors so they work together as a single logical entity. This provides high availability. If one node fails, others take over its workload, and often load balancing, distributing workload across nodes. Clusters can be active, all nodes run the service concurrently, improving performance and availability, or active-passive. Service runs on one primary node, passive node waits to take over only upon failure. Cloud bursting, revisited as FT. While often used for capacity, temporarily redirecting application load to a public cloud when private cloud resources fail or are overwhelmed can also be seen as a fault tolerance mechanism, ensuring service availability, perhaps for less critical applications. Network redundancy. This is critical. Techniques include link aggregation, combining multiple physical network links between two devices into a single logical link to increase bandwidth and provide failover if one physical link fails. NIC teaming. Grouping multiple physical network interface cards, NICs, in a server into a single logical NIC, again providing failover and sometimes bandwidth aggregation. Multipathing. Configuring compute systems to use multiple physical paths involving different host bus adapters, HBAs, switches, cables, storage controllers to reach storage systems. Software automatically manages path failover if one path breaks and can often balance I/O load across active paths. Storage fault tolerance. Storage systems themselves need redundancy. Traditional methods include RAID, redundant array of independent disks, or RAIN, redundant array of independent nodes. A more modern, space-efficient technique is erasure coding, which breaks data into fragments, encodes them with redundant information, and stores these fragments across different drives or even different nodes locations. It can often tolerate multiple simultaneous failures with less storage overhead than simple replication. We also see storage resiliency using virtualization, where storage virtualization appliance sits in front of different physical storage systems and mirrors logical volumes, LUNs, across them for high availability, independent of the underlying hardware. And even cache protection mechanisms ensure data temporarily stored in high-speed cache memory isn't lost if power fails before it's written to persistent storage. Service availability zones. This is about site-level redundancy, deploying multiple instances of a critical service across geographically dispersed but well-connected data centers or distinct zones within a cloud provider's region. If one entire zone or data center fails, due to power outage, network issue, etc., the service can continue running from the other zones. This requires seamless, often automated, failover mechanisms.
Okay, that's a lot of infrastructure resilience. What about making the applications themselves more fault tolerant?
That's equally important. Application resiliency techniques involve designing the software itself to handle failures gracefully, graceful degradation. Designing the application to maintain limited but essential functionality, even if some of its components or dependent services are unavailable. For example, an e-commerce app might still allow users to browse the product catalog, even if the payment gateway service is temporarily down, rather than just showing an error page. fault detect, and retry logic. Building logic directly into the application code to detect temporary errors, like intermittent network issues or a briefly unavailable service, and automatically retry the operation a few times before giving up and reporting an error. Persistent state model. Ensuring that critical application state is stored externally, e.g. in a database or distributed cache, rather than just in the memory of a single instance. This allows a new instance to start up after a failure and pick up processing from the last known consistent state. Checkpointing, periodically saving the complete state of a long-running application or process to persistent storage. If the application crashes, it can be restarted from the last successful checkpoint instead of having to start all over again.
These sophisticated techniques, both at the infrastructure and application level, are really what ensure our favorite cloud services stay online so reliably, often imperceptibly recovering from underlying issues, so we as users might never even know a problem occurred. Beyond keeping things running live, though, how do we protect our actual data from being lost permanently, right? Data is arguably the most valuable asset. How do we keep it safe and available, not just from temporary outages, but from permanent loss due to corruption, deletion, or disaster?
Data protection is absolutely critical, and it goes beyond just high availability. It's about making reliable copies of data specifically for the purpose of recovery or restoration if the original production data is lost, corrupted, or otherwise becomes unusable. Organizations often implement a tiered approach to data protection. This acknowledges that not all data has the same business value or requires the same level of protection. By categorizing data into tiers, e.g. Tier 1 for mission-critical data needing immediate recovery, Tier 2 for important business data needing recovery within hours, Tier 3 for non-critical data that can tolerate longer recovery times, organizations can apply different, cost-effective protection strategies to each tier. Data protection itself has evolved. We went from traditional server-centric backup, agent on every server, to snapshot-based backup approaches optimized for virtual machines, and now increasingly to cloud-based data protection strategies.
Let's talk about the core methods. Backup seems fundamental.
Backup and recovery is indeed fundamental. Its purpose is to create a secondary copy of data to secure it against loss and ensure its availability for restoration if the original data is lost or corrupted. A typical backup environment has three main components: the backup client, software running on the system being backed up; the backup server manages the backup process, scheduling, cataloging; and the backup target, where the backup copies are stored. This could be traditional tape drives, disk-based backup appliances, virtual tape libraries, VTLs, or increasingly cloud storage. For virtualized environments, image-level backup is very common. Instead of backing up individual files, it copies the entire virtual disk file and the configuration file of a VM as a single point-in-time VM image. This is very efficient for restoring an entire VM quickly. Most modern image-level backup tools can also perform granular file-level recovery from within the VM image. This process often offloads a backup processing workload from the production hypervisor host to a dedicated proxy server and typically uses VM snapshots to get a consistent copy. Another related concept is data archiving. This isn't backup for recovery, but rather the process of moving fixed, infrequently accessed data from expensive primary storage to lower-cost archive storage tier for long-term retention, often driven by compliance regulations or just to reclaim primary storage capacity. Archive data is still indexed and searchable, but takes longer to retrieve than data from backup. Private or public cloud storage is often used as an archive target.
Okay, backup and archive handle point-in-time copies. What about continuous protection or replicating live data?
That's where data replication comes in. It's about creating exact copies, replicas of data, often in near real time, typically at a secondary location. This is primarily used for achieving high availability, rapid failover to the replica, and business continuity, disaster recovery using the remote replica. There are different modes of replication. Synchronous replication. Writes from the compute system are committed to both the primary storage and the remote replica target before the acknowledgement is sent back to the compute system. This guarantees near zero data loss, a recovery point objective or RPO of 0 or near 0, because the remote copy is always identical to the primary. However, the need to wait for the remote acknowledgement adds latency, which can significantly impact application response time, especially over long distances. Asynchronous replication. Writes are acknowledged back to the compute system as soon as they are committed to the primary storage. The data is then transferred in batches or intervals to the remote replica site sometime later. This mitigates the application response time impact, making it suitable for longer distances, but it means there will be some data loss, a non-zero RPO, if a disaster occurs between replication intervals. Continuous data protection, CDP. This is a more advanced form of replication. CDP systems typically journal all data changes, allowing recovery not just to specific points in time, like snapshots, but potentially to any point in time within the journal's retention window. CDP can often operate in either synchronous or asynchronous modes depending on requirements. Cloud-based replication. Increasingly common is replicating application data and even entire VMs from an on-premise environment to the cloud, public or private, to mitigate risks associated with purely on-premise outages and provide a DR target.
With all this copying and replicating of data, volumes must get huge. A key technology for efficiency in data protection, especially with the explosion of data volumes, is deduplication, right? How does that work?
Yes. Data deduplication is incredibly important for making data protection economically feasible at scale. It's defined as the process of detecting and identifying unique data segments, often called chunks, within a given set of data to eliminate redundancy. Basically, it ensures that only unique data segments are stored. Subsequent occurrences of the same segment are replaced with just a small pointer to the already stored unique segment.
So storing data only once.
Essentially, yes, at a subfile level. The benefits are significant. It drastically reduces the amount of physical storage capacity required to store backup or archive data, often by factors of 10x, 20x, or even more, depending on the data type and retention period. This directly translates to reduced infrastructure costs for storage hardware, as well as associated costs like power and cooling. It enables organizations to retain backup data for longer periods within the same storage footprint. It often significantly reduces the backup window, the time it takes to complete backups, because less data needs to be physically written to the target. And especially with source-based deduplication, it dramatically reduces the amount of backup data that needs to be transmitted over the network. The effectiveness is usually expressed as a deduplication ratio, like 10.1 or 10x, meaning, for example, that 10 TB of original data only consumes 1 TB of physical storage space after deduplication. The actual ratio achieved varies based on factors like data type, change rate, and backup frequency.
Are there different ways deduplication is implemented?
Yes, there are two main types based on where the deduplication process occurs. Source-based deduplication. This eliminates redundant data segments at the source system, the backup client, before the data is transmitted over the network to the backup target. Its main advantage is significantly reducing network bandwidth consumption, which is great for backing up remote offices or laptops over slower links. Dell EMC Avamar is cited as an example using this approach. Target-based deduplication. This occurs at the backup device or target itself. Data is sent from the source, and the target appliance handles the deduplication. This can be done inline, deduplicating the data as it arrives before it's written to disk, or post-processing, data is stored temporarily first, then deduplicated later during idle periods. The main benefit here is offloading the processing overhead from the source system's clients. Dell EMC Data Domain is a well-known example of a target-based deduplication appliance.
Okay, that makes sense. And these sophisticated data protection techniques, backup, replication, dedupe, can often be consumed as services themselves, just like other cloud offerings.
Exactly. The cloud services model extends directly to data protection itself, offering convenience and potentially lower upfront costs for consumers. Backup as a service, BaaS, is where cloud service providers offer backup services, significantly reducing the consumer's overhead for purchasing, managing, and maintaining their own backup infrastructure and software. There are different deployment options. A local backup service might involve the provider managing the backup of consumer data that is already hosted within that provider's cloud. A remote backup service involves the consumer's data being transferred over the network from their on-premise location to the provider's backup infrastructure in the cloud. A replicated backup service might involve backing up data to one cloud location and then having the provider replicate that backup data to a secondary cloud location for added redundancy. This includes cloud-to-cloud backup scenarios. Regardless of the model, the service includes the ability for the consumer to easily recover data or VMs from the cloud when needed. Similarly, Disaster Recovery as a Service, DRAS, has emerged as a powerful offering. Here, the provider takes responsibility for providing the necessary compute, storage, and network resources required to run a consumer's critical IT services in the event of a declared disaster at the consumer's primary site.
So outsourcing the DR site.
Essentially, yes. This greatly reduces the need for the consumer to invest in and maintain their own expensive secondary DR site, which often sits idle most of the time. The typical process involves continuously replicating data, and maybe VM configurations, from the consumer's production environment to the DRS provider's location during normal operations. If a disaster is declared, the services are failed over and restarted at the provider's site, allowing the business to continue operating. Companies like Dell EMC offer an extensive suite of data protection products that embody these concepts. The source mentions Avamar, Data Domain, Networker, Mozy, Cloud Boost, Aperture, Recover Point, showing real-world implementations of backup, replication, deduplication, buys, and DRS.
It's clear that these services allow organizations to focus more on their core business, effectively outsourcing the complexity of designing, implementing, and managing robust data protection and disaster recovery solutions. We've covered a lot of the technical aspects of infrastructure and resilience, but you mentioned earlier that IT transformation is also deeply about people and processes. Let's dive into that side now. Right, let's switch gears a bit. We've been talking a lot about cloud technology, infrastructure, application security, but it's crucial to remind our listeners that successful IT transformation isn't just about the tech itself, is it? The human element seems just as important, if not more so.
That's a critical point to emphasize, and our source is very clear on this. It explicitly states that IT transformation does not come from technology alone. You can buy all the latest cloud technology, but if you don't change how people work and how processes operate, you won't get the full benefits. True transformation absolutely requires a fundamental transformation of IT operations, which is fundamentally about transforming the people who perform the work and the processes they follow to deliver value back to the business. The ultimate goal here isn't just adopting cloud, it's using cloud as an enabler to uncover new cost efficiencies, improve agility, and ultimately deliver differentiated business models and competitive advantage. This means the operating style, the culture of the organization itself must change. And this cultural change needs to be championed and led by business leaders, not just seen as an IT initiative.
So focusing on the people first, what about the existing IT workforce? Their roles and skills must need to change significantly in this new model, right? How do we cultivate a transformative culture and evolve existing skills?
This is a huge area and often one of the biggest challenges. Traditional IT skills, which might have focused on managing specific hardware silos like being a storage admin or a network admin or a server admin, need to evolve dramatically for a cloud service-oriented world. Staff must develop a broader understanding of the entire service lifecycle, the underlying technologies, automation, and critically, the needs of IT users and customers, and the overall business objectives IT is trying to support. Investing in targeted training programs is absolutely essential to upskill the existing workforce and bridge these gaps. Cloud adoption also often necessitates entirely new roles within the IT organization or significant changes to existing ones. Think about roles like service managers focused on SLAs and customer satisfaction, account managers interfacing with business units, cloud architects designing solutions, service operation managers overseeing the running environment, cloud engineers implementing and automating, DevOps engineers bridging development and operations, vendor relationship managers dealing with cloud providers, and cloud administrators managing the platform itself.
It sounds like breaking down silos is key.
Absolutely. Fostering a new way of working is crucial. This includes creating cross-functional teams, bringing people together from different traditional IT domains, and maybe even business units, with diverse expertise to work collaboratively on common goals or specific services. This often increases creativity and allows teams to be more self-directed and agile. And underpinning all of this, collaboration and communication become paramount. You need to break down those traditional departmental silos where teams might not talk to each other effectively. Teams need the right tools and maybe even physical facilities that encourage real-time chat, shared visibility, and continuous collaboration. Many DevOps tools, for instance, now integrate directly with communication systems like Slack to provide automated updates to stakeholders on build status or deployment progress. Think back to our broadcast satellite provider example again. Their physical shift from cubicles to collaborative pair programming stations wasn't just cosmetic. It was a deliberate move to embody and encourage this cultural change towards collaboration and faster feedback loops. It's really about investing in your human capital and fostering a new, more agile way of working.
So alongside transforming people and culture, processes must also undergo a significant transformation. Why are traditional IT processes like change management or provisioning often no longer sufficient in a cloud-driven world?
Traditional IT processes, often developed in the pre-cloud era, can frequently be inflexible, overly bureaucratic, and inefficient. This can lead to significant delays in delivering new IT services or resources. Imagine needing multiple levels of manual approval involving handoffs between several different siloed teams, server team, network team, storage team, just to provision a basic virtual machine. These delays directly inhibit the business agility that cloud promises.
Right. The process becomes the bottleneck.
Exactly. This creates a critical need for service automation. Automation is essential to overcome these challenges in service provisioning and ongoing management, allowing IT to achieve the speed and responsiveness required for business agility. It's about automating end-to-end processes wherever possible, from the initial self-service request in the service catalog all the way through provisioning, configuration, and even automated IT ticket resolution for common issues. The benefits of aggressive process automation are clear. Drastically reduce service provision time, minutes versus days, weeks, improve developer productivity, they get resources faster, reduced infrastructure management complexity and cost, less manual effort, and perhaps most importantly, a significant reduction in human errors that often occur during complex manual procedures. Continuous process improvement is also essential. It's not a one-time fix. Organizations need a mindset of constantly looking for ways to refine workflows, eliminate waste, and improve the quality of services and products delivered.
Are there standard frameworks that help guide this process transformation?
Yes, organizations often adopt or adapt established standard frameworks for guidance. ITIL, Information Technology Infrastructure Library, is a widely used framework for IT service management, ITSM, covering processes across the service lifecycle like service strategy, service design, service transition, service operation, which we discussed, and continual service improvement. Other frameworks like TOGAF, the Open Group Architecture Framework for Enterprise Architecture, or COBIT, Control Objectives for Information and Related Technologies for IT Governance, can also provide valuable structure. The key is adapting these frameworks to the speed and automation needed for cloud, not just implementing them rigidly. DevOps, which we discussed in the context of application development, is also a prime example of process transformation. It specifically aims to create a smooth, automated transition from development into operations, addressing common historical issues like undocumented configurations discovered only at deployment time or conflicts between development and production environments. Automation is absolutely critical for enabling effective DevOps practices, covering areas like configuration management, build automation, testing automation, and deployment automation.
Okay, transforming people and processes is key. Finally, how does cloud computing change the financial relationship between IT and the business? You mentioned IT moving beyond just being a cost center. How does that work in practice?
That's right. The financial aspect often undergoes a significant transformation as organizations mature their cloud adoption. IT aims to move from being perceived purely as an opaque cost center to becoming a transparent value provider, demonstrating how its services directly enable business outcomes. This is where concepts like chargeback and showback become crucial for financial transparency. Chargeback involves accurately measuring the consumption of cloud resources or services by each individual business unit or project, and then actually charging those costs back to them, typically on a monthly basis. This allows IT to operate more like an internal service provider with clear pricing, much like receiving a utility bill. It validates IT's value and makes business units directly accountable for the cost of the resources they consume.
And showback.
Showback is similar in that it involves measuring and reporting the costs of consumed services back to the business units, but without actually transferring funds or charging them directly. It provides the same level of transparency into consumption and costs, helping business units understand the financial impact of their IT usage, but without the complexities of implementing a full internal billing system. Showback is often used as a stepping stone towards implementing a full chargeback model later. There are several common chargeback models used in cloud environments. Pay-as-you-go. Charging based on actual metered usage, for example, per CPU hour per GB stored. Offers maximum flexibility but can be unpredictable. Subscription by time. Charging a fixed fee for a service for a specific period, for example, per month, per year. Predictable costs but might pay for unused capacity. Subscription by peak usage. Charging based on the highest level of usage reached during a period. Fixed cost prepay. Paying a fixed amount upfront for a certain allocation of resources. User-based, charging based on the number of users accessing a service, common for SaaS. Each model has different implications for cost control, budget predictability, and flexibility. The key benefit of both chargeback and showback is that they foster accountability and help business units make more informed decisions about their IT consumption, treating IT resources more like valuable assets rather than a free-for-all.
That makes a lot of sense. Linking cost directly to consumption drives better behavior. Now that we've successfully transformed people and processes alongside the technology, what tools are essential for actually managing these complex cloud services in this new transformed enterprise? Let's look at the toolkit. Okay, so we've navigated the complexities of digital transformation, covering everything from the initial imperative and technological shifts to the critical adjustments in people and processes. Now let's talk about the toolkit. After successfully transforming people and processes, what specific types of tools are essential for managing these dynamic cloud services and ensuring everything runs smoothly in this transformed enterprise?
Right. Having the right tools is absolutely essential to operationalize and sustain this transformation. You need robust tooling to effectively manage, monitor, and track all the cloud resources, ensure those critical service level agreements, SLAs, are being met consistently, and maintain the necessary availability and performance of the infrastructure and applications. The key is selecting tools that align well with your specific infrastructure choices, for example, public cloud, private cloud, hybrid specific vendors, your application architectures, microservices, traditional apps, and your chosen operating model, for example, DevOps practices, ITIL processes.
So it's not one size fits all. Let's maybe categorize some key types of tools that organizations typically use to manage this new landscape. We've touched on some functions already, but let's see how tools map to them.
Certainly. We can group these essential tools into several broad categories, each addressing critical aspects of cloud management and operations. First, you have your core cloud management tools or cloud management platforms, CMPs. These focus on managing the fundamental compute, storage, and networking resources within the cloud environment, whether it's public or private. They typically provide a unified management interface or dashboard. Examples mentioned in the source include OpenStack, popular open source platform for building private clouds, offering a dashboard for managing large resource pools. RightScale, a commercial platform providing a single console to manage resources across multiple public and private clouds. And the VMware vRealize suite, a comprehensive suite offering intelligent operations management, IT automation, and developer cloud capabilities across hybrid environments.
Okay, core management. What about automation? That seemed key.
Absolutely. Automation and orchestration tools are crucial. They automate the day-to-day operational tasks, complex provisioning workflows, and help manage configuration drift across large, complex environments. These are really the engines that enable the speed and consistency we talked about. Examples cited include Chef, uses a recipe-based approach to automate how infrastructure is built, deployed, and managed, embodying the infrastructure as code concept. Ansible, known for its relative simplicity and agentless architecture, used for IT automation tasks like configuration management, application deployment, and orchestration. Puppet, another major player in configuration management, helps automate infrastructure changes and manage configurations across servers using a declarative language.
And monitoring. Spend some time on that.
Yes, monitoring and alerting tools are vital for visibility. They collect performance metrics, logs, and event data from across the infrastructure and applications. They provide insights into system health, help optimize workloads, detect anomalies, predict future resource requirements, and trigger alerts when problems arise. Examples include Amazon CloudWatch, AWS's native service for monitoring AWS resources, collecting logs, and setting alarms, Dynatrace, a comprehensive application performance management (APM) tool that monitors user experience, application transactions, infrastructure, and uses AI for root cause detection. AppDynamics, another leading APM tool providing real-time visibility into application performance, end user experience, and even business transaction performance. Rackspace Monitoring, a service providing monitoring for infrastructure and applications across different cloud environments.
What about keeping track of the costs? Cloud bills can get complicated.
Very true. Cost management tools are becoming increasingly important. They help organizations manage their cloud usage costs, identify areas for optimization, like finding idle resources or suggesting better instance types, provide cost transparency back to the business, enabling showback chargeback, and assist with budget planning and forecasting. Examples include Cloudability, helps organizations understand their cloud spending patterns across multiple providers, allocate costs, and plan budgets. Park MyCloud, a tool specifically focused on automating the scheduling of cloud resources to turn them off during non-business hours to save costs. VMware vRealize Business for Cloud, part of the vRealize suite focused on providing cost transparency, consumption metering, and comparing costs across different cloud options. CloudCheckS offers optimization recommendations for public cloud usage, security checks, and helps implement chargeback models.
And finally, tools to help people work together better.
Exactly. Collaboration tools are essential for enabling teams, especially geographically dispersed or cross-functional ones, to work closer together, communicate in real time, and share information effectively. This is particularly important for supporting agile development and DevOps practices. Examples include Slack, a widely used platform for real-time team communication, channel-based discussions, and integration with other development and operations tools. Asana, a project and work management tool helping teams organize tasks, track progress, and turn conversations into actionable items. GitHub, GitLab, Bitbucket, platforms primarily for version control, Git, but also offering features for bug tracking, project management, CI/CD integration, and fostering social coding practices. Trello, a visual collaboration tool using boards, lists, and cards to organize projects and tasks, popular for its simplicity. And it's worth re-emphasizing, as the source does, that vendors like Dell EMC offer a broad portfolio of specific products that fit into these categories, building on their foundational infrastructure offerings like Cloudera for Storage Gateway, VxBlock for CI, VxRail and XC Series for HCI, ScaleI IO, and ECS for software-defined storage, powered servers for compute, with management and operations tools like OpenManage for servers, Boomi for integration, VIPR SRM for storage management, MyService 360 for support, Data Protection Advisor for backup monitoring, and integrations with platforms like vCenter Operations Management Suite.
It seems these tools really translate into tangible benefits, right? Drawing on those customer examples again.
Absolutely. Think back to the rental service company using Dell EMC VxRail, HCI. The integrated management tools and the nature of the HCI platform itself directly enabled that increased agility, higher performance for their VDI users, and drastically reduced administrative overhead compared to their previous traditional infrastructure. The right tools made the transformation achievable and sustainable.
These tools really are the essential toolkit then for navigating and truly thriving in this transformed IT landscape. You need the tech, the people, the process, and the right tools to manage it all. #outro. Wow, what an incredible journey we've taken today on the deep dive. We really covered a massive amount of ground, starting right at the beginning, exploring the absolute imperative of digital transformation and the urgency of digital disruption that's reshaping, well, pretty much every industry.
That's right. We delved into those core business and IT challenges that are really driving this need for fundamental change. And we spent time understanding IT's pivotal shift, moving away from just being technology-centric, focused on boxes and wires, to becoming a truly service-centric organization, focused on delivering value to the business.
Then we established that crucial foundational understanding of cloud computing itself. We started with the authoritative NIST definition, or common language, and then really unpacked its 5 essential characteristics: on-demand self-service, broad network access, resource pooling, rapid elasticity, and measured service. That's the very DNA of cloud, isn't it? We saw clearly how cloud acts as the great enabler for achieving that business agility and fostering innovation.
Absolutely. We then explored the various cloud models, how services are consumed. We looked at infrastructure as a service, IaaS, platform as a service, PaaS, software as a service, SaaS, and that broader category of everything as a service, SaaS, understanding the different levels of control and responsibility involved. And we examined the deployment models, public, private, community, and the increasingly important hybrid cloud, looking at its key use cases, alongside the pragmatic multi-cloud approach many organizations are taking.
Moving into the architecture, we looked at the cloud computing reference blueprint, providing that map. We focused heavily on how applications themselves have transformed, moving from traditional rigid monoliths to modern agile cloud-native designs. We touched on principles like the 12-factor app and architectural patterns like microservices, often packaged in containers. We saw how lean practices, agile methodologies, and especially DevOps with CI/CD pipelines are absolutely critical for accelerating application delivery.
And we didn't stop at the application layer. We dove deep into the modern infrastructure required to support all this. We explored the power of virtualization across compute, storage, and networks, which enables resource pooling. We traced the evolution towards the software-defined data center, SDI, abstracting and automating everything. We contrasted traditional build-your-own approaches with the simplicity and speed offered by converged CI and hyper-converged infrastructure, HCI, highlighting that really important strategic build versus buy decision every organization needs to make.
Then we tackled the critical importance of resilience. We covered business continuity planning and disaster recovery execution. We understood how to measure and achieve high availability, often expressed in those 9s, through implementing fault tolerance techniques at both the infrastructure level, like clustering and redundancy, and within the application design itself. And we explored the vital area of data protection solutions backup, archiving, and replication, including synchronous, asynchronous, and CDP methods, and how efficiency technologies like deduplication make this feasible. We even saw how backup and DR are now offered as a service.
Finally, and crucially, we circle back to the essential human and process side of IT transformation. We really emphasize that technology alone isn't enough. Success requires cultivating a transformative organizational culture, upskilling the existing workforce and embracing new roles, fostering cross-functional teams and collaboration, relentlessly pursuing process automation and continuous improvement, leveraging frameworks like ITIL and DevOps, and achieving financial transparency through models like chargeback and showback to demonstrate IT's value. And we tied it all together with an overview of the essential categories of tools needed to manage this entire transformed enterprise, from management and automation to monitoring, cost control, and collaboration.
It truly is a holistic journey. And as we wrap up today's deep dive, maybe the key takeaway is just that. Digital transformation enabled by cloud is about reshaping your entire operating model. It's not just about adopting new technology. It's fundamentally about transforming your people, your processes, and the underlying culture to truly harness the power of cloud computing for sustained business agility, continuous innovation, and real competitive advantage.
Well said. It's the synergy of all those elements.
So as you, our listener, reflect on this extensive discussion, perhaps consider this. What aspects of digital transformation or cloud adoption that we've talked about today resonate most strongly with your current challenges or aspirations? How might applying these principles, focusing on delivering services, embracing agility, automating processes, empowering your teams, ensuring resilience, reshape your own organization's future or even your own role within it? We encourage you to mull on that. Thank you so much for joining us on this incredibly deep dive into digital transformation and cloud foundations. Until next time, keep digging.